Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module we will continue the discussion of varying the angle of incidence and then looking at what happens to the reflection from transverse magnetic and transverse electric polarized waves. So, we have already seen that transverse magnetic case actually we have at a particular angle called as Brewster angle, the reflection goes to 0, which means the wave does not reflect back anything, but transmits completely into the second medium. Okay. So, this angle Brewster angle theta b, I did not give the expression for that and I did not want to derive it, but the expression for that is given by tan inverse of n2 by n1. So, for the previous case of n1 equals 1 and n2 equals 1.44, this angle works roughly around 34 degrees. Okay. You can actually use a calculator and actually calculate that one. Now, what we want to do is to reverse the situation. So, earlier what we had considered was n1 is 1 and n2 is 1.44. So, what we had was say, so this is n1 and this is n2. So, this is the medium. This time I am going to consider not the transverse magnetic case that we have been considering, but transverse electric case. The reason I am considering transverse electric case is because in the transverse electric case, electric field is oriented along the y direction for incident, reflected and transmitted waves. That way I do not have to decompose the vector electric field vector in my expressions. Of course, with a little bit of more effort from my side, I could have considered the transverse magnetic polarization for the discussion of total internal reflection, because there would just be one more component of the electric field that would be present, but I am not going to do that one. I want to keep my life little bit simple. So, I will choose transverse electric polarization. The ideas of course are easily transferable to transverse magnetic polarization. So, this is a situation that we are now quite familiar with since the last 2-3 modules. We have a wave incident at an angle theta I and the wave which is now transmitted at an angle theta t. I am not interested in the reflected wave at this point, I am only interested in the transmitted wave, but now with a very important consideration that n1 happens to be greater than n2. For example, this could be fused silica 1.44 refractive index and this could be air. So, you now have a situation where you are moving from what is called as the denser medium to rarer medium. So, remember denser and rarer only refer to the refractive index values. The larger the refractive index, we call this as the denser medium, the smaller one we call as the rarer medium. And what am I interested, as I told you, I am interested in the transmitted wave, which of course makes an angle theta t. What is the bounds on theta t? I mean, as I increase theta I, on what values of theta t can, or what values of theta t can it take? I have theta t equal to 0. So, in that case theta I is also 0, in that case theta t will be equal to 0, and this k vector of the transmitted wave would be lined up nicely along the z axis. On the other hand, I would expect as theta I starts to increase that this angle theta t changes, and at most it should change by 90 degrees, right. Is our intuition correct? In this case where we are moving from denser to rarer, of course our intuition is wrong, because there exists what is called as a critical angle. Okay. So, once your light is incident at an angle great or at an angle critical angle as what we would call it, the ray would actually, the transmitted ray would actually start propagating along the interface, and next time when you increase the angle of incidence beyond this critical angle, then we have observed from our experience that there will be a reversal of the wave. The transmitted wave actually gets reflected or goes back into the first medium, it will not go to the second medium at all. So, purely from theta t value, this has now increased beyond 90 degrees, right. So, up to this is 90 degrees, and once this angle of incidence is increased beyond the critical angle, mathematically at least theta t has increased beyond 90 degrees. Okay. When this happens, what would be the expression for I mean whether this can happen with all the considerations that we have, and what is the condition that needs to be satisfied for this one is what we want to see now. Okay. So, let us focus our attention on the transmitted electric field expression. There I have, since this is a transverse electric case, I have used the transmission coefficient for the transverse electric case. So, the expression for the electric field vector, which would be oriented along the y axis, will be given by tau T e, which is the transmission coefficient, times y hat, okay. And I am assuming that the incident amplitude, the amplitude of the incident wave is equal to 1. Otherwise, I should write down this incident amplitude as well, so which I do not want to write it. Okay. So, with normalized values, what we have is the transmission coefficient tau T e, which of course will be in magnitude less than 1, or will it be? Let us see that. So, this fellow will be times e power minus j k t 0 sin theta t x plus cos theta t times z. Okay. And we also know that cos theta t can be written as 1 minus n 1 square sin square theta I divided by n 2 square under root. Now, observe that we have a situation where n 1 is actually greater than n 2, correct. Our incident medium happens to be optically denser compared to the rarer medium. Okay. And if you plot theta I as a function as this one, and then if you look at the reflection coefficient for the transverse electric case, the magnitude of the transverse of the reflection coefficient for the transverse electric polarized wave, then at 0 of course, it starts off with some value, okay, and then what you would see is very different from what you would expect. So, what you actually see is that while it continues to grow in magnitude, at some point it suddenly becomes 1 and stays 1 thereafter. So, this is what is called as the critical angle. And if you were to do the same thing for the transverse magnetic case, you would see that initially it would start at the same value as T e, in magnitude of course they are the same, but then goes through a 0, right, which is where you would have the Brewster angle value, and then suddenly shoots up to a magnitude of 1 and continues to remain there, okay, and it will do so at exactly the same angle as the T e case. This is interesting, both T m and T e cases actually exhibit the same critical angle. The value of the critical angle is independent of what polarization of light that you have transmitted. So, if you had initially both T e and T m, right. So, if you had both T e and T m, the moment you have the critical angle, the output would also be T e plus T m. Okay. So, no T e or T m actually escapes, and the magnitude of the reflection coefficient will be completely in this particular way. So, it would actually be equal to 1, okay. But that does not mean the transmission coefficient will also be equal to 0. That is an interesting part. Normally one would expect that if the wave is actually completely reflected and we say that there is nothing in the second medium, this is what our traditional theory of total internal reflection would say, but it is not true. What you would actually have is a very interesting phenomena which we are going to talk about it now. Okay. So, this I hope you can write a short MATLAB script, or you can use Excel and then show that this magnitude of T e or magnitude of T m, both cases would actually exhibit this type of a behavior. That is, there is a critical angle beyond which the magnitude of the reflection coefficient will remain equal to 1. Okay. But what happens to the expression for the transmitted field? Well, look at the transmitted field expression, right. I have this e to the power minus j k t dot r, and I know that k t, the transmitted wave vector, is given by k t 0 x hat sin theta t plus z hat cos theta t. That comes simply by decomposing this k t vector, right. So, you decompose this k t vector into horizontal x component, which would be sin of theta t, and the vertical component along z axis, which would be cosine of theta t along z axis. So, this expression I hope you know, and of course, this expression for k t 0, which is the magnitude of the wave vector in the second medium, will of course be equal to k 0 times n 2. Okay. Now, go back to this expression of cos theta t and substitute that expression into the electric field expression. Okay. I am going to do that one in this next slide, and what I have will be the transmitted electric field being directed along the y axis, tau T e y hat e power minus j k 0 n 2 sin theta t x, and I am going to just split the exponential function. Okay. So, I will have e power minus j k 0 n 2 square root of 1 minus n 1 square sin square theta I, okay, divided by n2 square times z. So, please remember that we have a situation that n1 is actually greater than n2, and what is our Snell's law? N1 sin theta I is equal to n2 sin theta t. Now, look at this, theta I is a component which is increasing, going from 0 to 90 degrees. So, when theta I is equal to 0, of course, this entire left hand side will be 0, right hand side will also be 0, and when theta I starts to increase from 0 to 90 degrees, at some point, right, the product n1 and sin theta I can actually be greater than the product n2 sin theta t, right. Why would that happen? Because n2 is smaller and maximum value of sin theta t could be equal to 1, and therefore, the maximum value that the right hand side can take in this expression will be equal to n2. Whereas, on the left hand side the maximum value that it can take is n1, but you may not even need to go all the way up to theta equal to 90 degrees to reach the maximum. Okay. This is in some sense, if you go from 0 to 90 degrees and plot this n1 sin theta I. So, if you plot this n1 sin theta I, it would look something like this, reaching a maximum of n1, okay, as theta I is increased, and theta t would also be changing to keep pace with this expression, right. So, because these two expressions have to be equal for all values of theta and theta t as per our expectation. So, depending on theta I, theta t increases faster, because it is one which actually has a smaller value of n2 to compensate for the larger value of n1 here, and at some point, okay, it just cannot. So, I am not able to write this one. So, let us say I am trying my best here. At some point, actually it goes slightly like this. So, this is what would happen for n1 and this is what would happen for n2. So, the angle theta t must change rapidly, but at some point it hits n2, or rather it actually hits n2 at this point, but then it will not be sufficient for this one to be equal to the left hand side. So, perhaps this figure did not convey what I wanted to try or what I wanted to write down, but you get the idea, right. See, theta I is changing, okay, and theta t is changing at a much faster rate, because or much faster value compared to theta I, because the product of these two should be equal to the product on the left hand side, but at some critical angle it just so happens that n1 sin theta I c would be equal to n2, and if your angle of incidence becomes greater than critical angle, then this product would become greater than n2, and you just cannot have a real value for theta t. So, no real value of theta t can actually satisfy this particular requirement, and in that case what happens is that total internal reflection takes place, theta t mathematically becomes greater than 90 degrees, okay, and then the wave actually reflects back into the first medium. This is what the total internal reflection phenomenon is. But what happens to the electric field amplitude? Well, if you go to this one, now at theta I equals theta c, and this numerator n1 sin theta I is equal to the denominator n2, and therefore, this one will be 1, and the exponential term with respect to z will be equal to 1, and what you now are left is an expression which is just dependent on x, right. So, let us do this. At theta I equals theta I c, n1 sin theta I c will be equal to n2, because theta t would have become 90 degrees and it cannot really go beyond this 90 degrees. So, in that case this expression for the z will be, this multiplier for z will be 0, and this one will be equal to 1, the exponential will be equal to 1, and the electric field would be y hat tau t e. Okay. We should of course also look at what happens to tau t e at theta I or theta t equal to 90 degrees and theta I equal to this one. Okay. In any case, I will not do that one, I am interested more in this second part which I will come to it. So, this will be e power minus j k 0 n 2 sin theta t times x. What kind of a expression for this electric field is this? This is an expression for an electric field which is now travelling along the plus x direction. Now, what is plus x direction? Well, we had this as the x axis, right, this was the z axis, this was the interface. So, what we have is that when the incident angle happens to be exactly equal to the critical angle, the wave that we now have is actually a x propagating wave. So, this is a wave which is propagating along the x axis, very interesting, right. So, this wave is propagating along the x axis, the corresponding k vector along the x direction is given by k0 n2 sin theta t, okay. And the lambda along the x axis for the wave which is propagating now will be given by 2 pi by k0 n2 sin theta t. 2 pi by k0 is the free space wavelength lambda 0. So, this is lambda 0 divided by n2 sin theta t, okay. Sin theta t will be equal to 1 in this case, and therefore, this is what you would actually have. So, lambda 0 by n2. So, it is very interesting that the wave is actually propagating along the interface at theta I equal to theta IC. What happens when theta I is greater than theta IC? Then this expression n1 sin square theta I becomes greater than n2, right, and therefore, this term becomes greater than 1, and the square root of a number. So, the number becomes negative, the radical inside the square root becomes negative, and overall this will become complex, okay. And if this is complex, then you can rewrite this as plus or minus j alpha, where alpha is given by square root of n1 square sin square theta I divided by n2 square minus 1, okay. So, should I choose plus j alpha or minus j alpha? Now, physically what I know is that if I move far away into the interface, that is far away from the interface, I should not expect any energy, nor I should not expect any waves, right. So, these waves should actually go to 0. So, if I had e power minus j some number k0 n2, and if I choose plus j alpha, right, then j and minus j would actually become positive, and this fellow would actually grow along with z. Therefore, the correct sign that we need to choose for this alpha is that of a minus sign. So, I have minus j alpha. So, I can rewrite this quantity once theta I is greater than theta IC into this form, and then alpha will be equal to this expression. So, the electric field would become tau T e power minus j k x x, where k x is the wave vector k0 n2 sin theta t. Of course, sin theta t will be equal to this one, you can calculate it, k e power minus j k x x times e to the power minus alpha z, and it is this alpha which tells you how quickly the wave would decay as you move away from the interface. So, this is the interface that we have, okay, and then as the wave which was propagating along the interface, okay, for the critical angle, once you increase the angle of incidence beyond critical angle, the wave would still be a travelling wave along the direction of the interface, but it would actually start to decay along the direction perpendicular to the interface. So, maybe as you go to the interface, this would essentially decay out, and it would decay out in a manner which is exponential with a decay parameter of alpha, right. So, as you move away and away, the wave is decaying further and further, but propagating along the interface, okay. Such a wave is called as evanescent waves, okay. The great importance of evanescent wave is that I could, for example, have a slab waveguide. This was earlier done this way, and then I could have a prism or something, and then I have light incident on it. This light would be incident in such a way that this is air or some other lower refractive index material, and this would be incident at an angle which is greater than the critical angle. Therefore, the wave would be completely reflected and it would be available back to the source, okay. So, this is the light source in that we are sending in, and this is the slab waveguide, which is one of the important optoelectronic device that is used to guide light, and because this is angle greater than the critical angle, there will be a decaying wave. So, there will be a propagating, but there will be a decaying wave along the direction perpendicular to the interface, okay. And some of that wave, if you can adjust the gap between the prism and the slab waveguide, some of that wave can actually just be sufficient to generate or excite a mode inside this slab waveguide, which would then be picked up and the corresponding mode would propagate, okay. So, it is just used to excite the mode inside a slab waveguide, and this is form of coupling is known as a prism coupling, which was very popular, even now it is quite popular to excite light into the waveguides, okay. So, this waveguide light that is being excited is actually in the form of this evanescent wave. So, the evanescent wave, although we can show that it does not really carry any power in the direction perpendicular to the interface, it still can excite waves because it does not really go off to 0. So, the wave will not go off to 0. What does go to 0 is the energy which is perpendicular to the direction of the propagation. Okay. And as the angle of incidence is greater than critical angle beyond very large value, then the rate of decay would also be quite large. The value of alpha would also be quite large. Okay. So, this is what goes in behind the scenes of a total internal reflection phenomenon. So, it is not just sufficient for us to say that when angle of incidence is greater than the critical angle, the entire light gets reflected and nothing is transmitted onto the other side. In fact, very important devices are based on the fact that there is an evanescent field onto the other medium. Of course, that evanescent field would not be propagating perpendicular to the interface, they would be propagating parallel to the interface, along the interface, and they would decay along perpendicularly to the interface, but they are useful in cases, many cases. One of them was to excite the modes. This is not the complete story. There is one additional story that I would like to talk about total internal reflection. Well, if we go back to the expressions of say gamma TE or gamma TM, right. So, let us go to the expression for gamma TE, which is given by N1 cos theta I minus N2 cos theta t divided by N1 cos theta I plus N2 cos theta t. Okay. We consider the situation where the angle of incidence is greater than the critical angle. So, obviously, in that case cos theta t would actually have become complex. Cos theta t is actually what we wrote as minus j alpha, where alpha is equal to square root of N1 square sin square theta I divided by N2 square. Okay. So, minus 1 of course. So, this is what we wrote. This theta I times N1 remains real quantity. So, what we have for gamma TE will be some real quantity plus j alpha because of a minus and minus becoming plus there. Then you have N1 cos theta I minus j alpha. If I have A plus JB, the corresponding polar form will be the magnitude quantity, which is say square root of A square plus B square, times the phase, which is plus j tan inverse of B by A. Okay. I am assuming certain things about B and A, that they will be positive, and therefore, you do not really need to worry about which quadrant or add a certain pi or something like that. Okay. But in any way, you can always represent a complex number in terms of its magnitude and an angle, the so called polar form, and because gamma TE happens to be of the form A plus JB divided by its conjugate A minus JB, the magnitude of the numerator will be equal to the magnitude of the denominator. The phase of the numerator will be minus or negative or shifted by 180 degrees for the phase of the denominator, because one of them is conjugate of the other, right. So, I can write A minus JB as the same magnitude, but with a phase which is minus j tan inverse of B by A, right. Now, I go back and write the numerator and denominator in this fashion, and because the magnitude is the same, that would cancel out with respect to each other, and what I have is e power j phi divided by e power minus j phi. Together this becomes e power j 2 phi. Okay. And you can call this e power j 2 phi as some psi with a TE, and this particular psi with a TE is what is called as the phase shift upon reflection. So, when total internal reflection happens, it not only pushes, not only reflects all of the light back into the first medium. Okay. There is evanescent wave in the other medium of course, but the reflected light would have a certain phase shift or would undergo a certain phase shift, which of course is dependent on what is this value theta I and the value of alpha. So, this expression for phase shift upon total internal reflection, see this is different from phase shift upon reflection of a typical TE or TM case, and for the TE case you can show that this would be equal to 2 times tan inverse of square root of N1 what we had was N1 square sin square theta I minus n2 square divided by n1 cos theta I, or with a minus sign of course. So, and since minus of tan is the same, so this can be pulled out and then you can put a minus sign back onto this one. So, this is the expression. Of course, this expression simply comes from this case, right. So, you would have n1 cos theta I plus j alpha. So, you can express this one. So, it would be tan inverse of alpha divided by n1 cos theta I. There will be denominator as well, which would be tan inverse of minus alpha divided by n1 cos theta I, and then you can put both of them together and then you would have the sum of these two. So, tan inverse of A plus tan inverse of minus A, and then you can use all those formulas with them. Sorry, there is a minus sign here, not on the outside, and you can use those formulas and then find out that the total phase shift for the transverse electric case will be this expression. There is a very important point which I will finally mention and then leave it out here. So, what we have done is that, let us suppose that we had a lower refractive index medium here, okay, and then we have a higher refractive index medium, okay. And what we have done is a very interesting case. So, this is a normal to the interface as such. By carefully taking the angle of incidence to be greater than the critical angle, what I have done is to essentially reflect all of my light back into the first medium, right. So, of course, there will be evanescent wave, but the evanescent waves are not carrying any energy, right. So, there is no power transfer that is happening because of the evanescent waves. But what I have achieved is a very remarkable thing. When light is incident at an angle, the entire light getting reflected back, okay, means that if I can somehow engineer another layer of interface here with a lower refractive index and cause this ray or this wave also to be at an angle greater than critical angle, then this light would be reflected further back into this wave, right. There will of course be an evanescent wave which has no meaning, but this would be reflected back. In essence, what I have done is to confine this light into this slab of higher refractive index, and I have done it without any use of a mirror, okay. So, we will expand upon more on these type of devices in the next module. Until then, thank you very much.